Welcome to our exploration of Lagrange multipliers, a powerful technique for finding maximum and minimum values of functions subject to constraints. We'll break down this method step by step with clear visuals and an intuitive example. Let's start by understanding what problem we're trying to solve. We want to maximize or minimize a function f of x and y subject to a constraint g of x and y equals 0. For example, we might want to find the largest and smallest values of f of x, y equals x times y, given that x squared plus y squared equals 1. The key insight of Lagrange multipliers is that at an extreme point on a constraint, the gradient of our function f is parallel to the gradient of the constraint g. Mathematically, this means that the gradient of f equals lambda times the gradient of g, where lambda is a new variable called the Lagrange multiplier. Let's visualize what this means geometrically. Imagine our constraint g of x, y equals 0 as a curve in the xy plane. The function f of x, y can be visualized as contours, where each contour represents points with the same function value. At the maximum or minimum value of f on our constraint curve, the contour of f is tangent to our constraint curve. This means the gradients, which are perpendicular to the contours, must be parallel at that point, which is exactly what the Lagrange condition states. Now, let's outline a step-by-step recipe for solving problems using Lagrange multipliers. First, compute the partial derivatives of both f and g with respect to x and y. Second, set up the Lagrange equations. F sub x equals lambda times g sub x. F sub y equals lambda times g sub y. And don't forget the constraint g equals 0. Third, solve these three equations for x, y, and lambda. Fourth, evaluate f at each solution point. Finally, compare the values to determine which are maxima or minima. Let's apply this method to our example. Maximize and minimize f of x. Y equals x times y subject to x squared plus y squared equals 1. We'll go through all 5 steps systematically. Step 1. Compute the gradients. The gradient of f is the partial derivatives. F sub x equals y, and f sub y equals x. The gradient of g is g sub x equals 2x, and g sub y equals 2y. Step 2. Set up the Lagrange equations. We have y equals lambda times 2x, and x equals lambda times 2y, plus our constraint x squared plus y squared equals 1. We can simplify these first 2 equations as y equals 2 lambda x and x equals 2 lambda y. Step 3. Solve the system. From the first equation, if x is not 0, we can write lambda as y divided by 2x. From the second equation, if y is not 0, lambda equals x divided by 2y. These must be equal, so y divided by 2x equals x divided by 2y. Simplifying, we get y squared equals x squared, which means y equals plus or minus x. Now, we substitute into our constraint. If y equals x, then 2x squared equals 1. So x equals plus or minus 1 over square root of 2. And y has the same value. If y equals negative x, we also get x equals plus or minus 1 over square root of 2, but now y equals negative x. Step 4. Evaluate the function at each candidate point. We have 4 possible points. 1. X equals 1 over root 2. Y equals 1 over root 2, 2. X equals negative 1 over root 2. Y equals negative 1 over root 2, 3. X equals 1 over root 2. Y equals negative 1 over root 2, 4. X equals negative 1 over root 2. Y equals 1 over root 2. Let's evaluate f of x. Y equals x times y at each point. At the first point, f equals 1 over root 2 times 1 over root 2, which equals 1/2. At the second point, f equals negative 1 over root 2 times negative 1 over root 2, which also equals 1/2. At the third point, f equals 1 over root 2 times negative 1 over root 2, which equals negative 1/2. At the fourth point, f equals negative 1 over root 2 times 1 over root 2, which also equals negative 1/2. Step 5. compare the values to determine maxima and minima. We found that the maximum value of f is 1/2, which occurs at the points where both x and y have the same sign. The minimum value is -1/2, occurring at points where x and y have opposite signs. Let's visualize these points on our constraint circle. To summarize the Lagrange multiplier method, first, we form the system of equations by setting the gradient of f equal to lambda times the gradient of g plus the constraint equation. Second, we solve all these equations together to find the critical points. Third, we check all these points on the constraint. Finally, we compare function values to determine which are maxima and which are minima. This powerful technique allows us to find extrema of functions subject to constraints, which is essential in many areas of mathematics, physics, economics, and engineering. Thank you for watching.